This video is a final reminder of all the topics that you need for Physics Paper 2 of AQA GCSE Combined Science. If you're taking the foundation tier, then watch out for the headers on each slide because these change colour and say higher tier only if it's a topic that you can skip. By now you're hopefully aware of all of these things, but just as a final reminder, it's really important that you write in black pen and stay inside the answer boxes because your exam paper is going to be scanned. Watch out particularly on this paper for sneaky units that you might need to convert. We're especially expecting the exam board to give you masses in grams, which need to be turned into kilograms, and also distances in centimetres, micrometres or nanometres, which you need to convert to metres. Remember that for any kind of extended response question, it's absolutely encouraged to give your answer in the form of bullet points. This is going to save you time, make your answer clearer, and there are no marks at all in GCSE Science for writing in full sentences. If you see the command word evaluate, you need to be making comparative statements about the data you've been given. So say this one is 5 times bigger or this one is 2 times smaller. Also, you must make sure that you write a conclusion because for a 6-mark evaluate question, you can't get the final 2 marks without doing this. If you have to write the method for a practical, make sure that you've done this in a logical order, and I'd strongly suggest using bullet points or a numbered list. At the end, read it through and make sure that somebody could follow your exact method and still get all the data they need to answer the question. Remember that your working scientifically skills are going to be assessed as well as your physics knowledge, so you should know the difference between repeatable and reproducible data, be able to talk about the resolution of your equipment, and how computerised methods of data collection are more accurate, rapid and sensitive. Don't forget that if you're translating data from a graph into a table, it's really important to make sure you've plotted all of the points, even if one of them is at the origin. Remember that when your maths teacher says that a line of best fit has to be straight, they mean in GCSE maths, not in the real world and not in your GCSE science exams. So if your data curves, make sure that your line of best fit curves too. 30% of the marks in GCSE physics are for mathematical skills, so it's really important that you've made sure you're comfortable with all of these. This includes skills like substituting and rearranging equations, but also standard form, giving your answer to the correct number of significant figures, and plotting graphs. You can find a full list of everything you could be assessed on in Chapter 9 of the specification, so make sure that you've had a quick look at this before the exam and that there's nothing in there that's going to completely throw you. While it's true that in 2023 students are going to be given a copy of the equation sheet in the exams, this sheet only contains each equation in a single format. So if you're not very confident in rearranging equations under pressure, it may be worth memorising the rearranged versions of these equations, particularly more complex ones like the one involving final velocity, initial velocity and acceleration. It's also important that for each quantity you know the units, partly because this may come up as a 1-mark question, like state the units for magnetic flux density, but also because you may be asked to do a calculation where they don't specify this number is current, they just give you a number in amps and expect you to know that. So to start with a few straightforward ones, you should know that all forces, including weight, are measured in newtons, and that all masses must be in kilograms. Distances must be measured in metres, and speeds or velocities are in metres per second. Then we've also got times in seconds, and then we can start to fill in some of the gaps. So we've got gravitational field strength in newtons per kilogram. Work done is a measure of energy, so that's in joules. Acceleration is in metres per second squared, and remember that squared is part of the unit. It doesn't imply that you need to do any squaring on your calculator of any of the numbers. Then if mass is in kilograms and velocity is in metres per second, momentum can be found by multiplying those two together, so we get kilogram metres per second. Then frequency is in hertz, magnetic flux density is in teslas, current is in amps, and potential difference is in volts, and current, as we've already said, is in amps. Within physics, we like to separate quantities into scalar quantities and vector quantities. Scalar quantities are ones which don't have a particular direction, they just have a magnitude, or in other words, a size. This includes things like temperature, energy, and speed. Then vector quantities are ones which have both a magnitude and a direction. This includes velocity, momentum, and also forces. Vectors, including forces, can be represented by arrows, where the length of the arrow corresponds to the size of the particular force, and the direction of the arrow tells you what direction it's acting in. We can use these to draw free body diagrams. The idea of a free body diagram is there's no sense wasting time drawing a car or a boat, so instead we just have a small circle at the centre to represent the centre of mass, and then the arrows go off this, showing the forces that are acting on a particular object. All forces in the world can be split into contact and non-contact forces. Contact means touching, so a contact force is one that only exists if the objects are touching each other. A non-contact force can exist even when objects don't touch each other, but that doesn't mean it goes away just because they are touching. You still have a weight, which is caused by gravity, even if you jump out of a plane, so weight is a non-contact force. But we don't suddenly start describing weight as a contact force when you're stood on the ground. It can and does exist both when you're touching the earth and when you're not, so we always describe it as a non-contact force. We've just named weight as one example of a non-contact force. Electrostatic forces occur between objects with a positive and a negative charge. You also know about magnetic forces, which allow magnets to attract materials that are made of iron, cobalt and nickel. The four contact forces which you should be able to name are friction, which occurs when objects rub together, air resistance, tension, and normal contact force, which is the force that objects exert in order to stop other objects from pushing through them. Here, the book is pushing down on the table due to its weight, and then the normal contact force from the table is pushing back. Newton's third law says that for every action there is an equal and opposite reaction. This means that forces always come in pairs, and there are four things that are always true about the pair. The first thing is that the two forces are always of equal size. So if we take our example just there of the book pushing down on the book is pushing down on the table with a force that is equal in size to the force with which the table is pushing back on the book. This must be true because if the force of the book pushing down was bigger, then the book would fall through the table. And if the force of the table pushing back on the book was bigger, then the book would be levitating, and neither of those things is true. The second thing is they must both be the same type of force, so either they're both pushes or they're both pulls. You never have an interaction pair where one is a push and one is a pull. Thirdly, the forces are acting in opposite directions, so the book is pushing down and the table is pushing up. Finally, they're always acting on the other object. So the book is pushing down on the table and the table is pushing up on the book. The words mass and weight are often incorrectly used interchangeably. Mass tells us how much matter or how many atoms an object is made from. So this square here is made up from 56 atoms. Mass is measured in kilograms and the shorthand for that is kg. It isn't affected by forces, so your mass doesn't change because somebody pushes you or because you're experiencing air resistance. It also doesn't depend on where you are. Just because my dino has moved from the Earth to the Moon doesn't mean his mass has changed, because he's still made of the same number of atoms. Any object with mass entering a gravitational field experiences a force called weight, which is measured in newtons. Gravity doesn't just affect planets or other really big objects like the Moon, but the strength of a gravitational field is determined by the mass of an object. So because Earth is so much bigger than you are, Earth's gravity is about 10 to 24 times bigger than yours, and so you don't really notice yourself having gravity because the Earth's gravity is so much bigger. Now this is important because the stronger gravity is, the larger the weight of an object will be. And this is important because this causes changes in motion. For instance, you've probably seen videos of astronauts jumping on the Moon, and because their weight is small, because the gravitational field strength of the Moon is small, they can jump higher and they can jump further than they could on the Earth. To link back to our earlier point, scalar quantities don't have a direction, they only have a magnitude, so mass is an example of a scalar quantity, whereas weight is a vector quantity because your weight has a direction, it's pulling you down towards the Earth. Weight can be measured using a piece of equipment called a calibrated spring balance or a Newton meter. This contains a spring which stretches as a larger force is applied. This causes a marker to move, allowing us to read the size of the force. An object with a bigger mass also has a bigger weight, so it will trigger a bigger reading on the Newton meter. In fact, we can even go slightly further than just saying as one increases, the other increases. Weight and mass are directly proportional, which means that as mass doubles, weight doubles too. This means if we plot them both on a graph, we see a straight line which passes through the origin, or 0, 0. Objects never have one single force acting on them, even if the forces are basically invisible and we can't see them acting right now. If we try to use all of the different forces acting on an object to predict how it's going to move, this can be quite complicated, but we can often simplify these forces into resultant forces, which you can think of like an overall force. Basically, what we're going to do is we're going to add up forces that are working in the same direction and subtract forces which are working in the opposite direction. And this is going to make it simpler for us to identify what is going to happen to an object's motion. For instance, my box here has two equal and opposite forces acting on it. So the resultant force is 0 newtons. And this means that the box is going to move in exactly the same way as if there were no forces acting on it at all. In the example shown by this free body diagram, I've now got two opposite forces pulling in opposite directions. You can think of the right-hand force as being made up of 60 newtons, that is opposing the left-hand force, and then another 40 added on. So the overall force that's acting, the resultant force, is 40 newtons to the right. Similarly, if I have two different forces which are acting in the same direction, I can just add them together to give me the resultant force, which here would be 160 newtons. If you're taking the higher tier paper, then you may encounter questions like this one, which asks you to work out what the resultant force is for two forces that are not acting in the same plane. So they're not acting opposite to each other or in the same direction, they're going off in completely different directions. And the only way that you can do this is by drawing a scale diagram. And for that, you absolutely have to have a protractor, so make sure you do have one with you for physics paper 2. So firstly, you need to pick a sensible scale. In this question, I would probably pick 1 centimetre representing 10 newtons. So the first thing I would do is draw one vector that was 10 centimetres long to represent my 100 newton force, and then I'd use my protractor to measure an angle of 64 degrees, and then draw a second 5 centimetre long line to represent my force of 50 newtons. Then, having drawn those two lines, I'm going to make those two sides of a parallelogram, and I'm going to fill in the rest of the parallelogram. Then I'm going to draw a diagonal line that goes across that parallelogram from one corner to the opposite corner. And provided that I've done my scale properly and I've drawn the diagram properly, by measuring the length of that line, I can find out what the size of the resultant force will be. If the pair of forces are acting perpendicular to one another, then it is possible to answer the question by using trigonometry rather than a scale diagram. But watch out, because if the question says draw a scale diagram to work out the size of the resultant force, then there will be working marks for drawing it. And if you've solved the question using trigonometry, then you won't get those marks. Although it is absolutely fine if you want to use trig in order to check the answer that you've come up with. So we start off in the same way. We draw our scale diagram, setting our scale beforehand as something sensible like 10 newtons per centimetre. And then we turn this into a parallelogram, which in this instance is of course just a rectangle, and then draw in the diagonal. And by measuring the length of that diagonal, we can work out what the size of that resultant force is. So you can then measure using your protractor to see what the bearing is. It would also be possible to solve this using Pythagoras theorem and then work out what the inverse tan is in order to work out what the degree of the bearing is. Almost certainly the most challenging thing you can be asked to do in this forces part of the exam is to separate a diagonal resultant force into its perpendicular components. The first thing that we need to do is to start drawing our scale diagram, and to begin with, I'm not really interested in the length of the lines, I just want to get that 30-degree angle. So I'm going to draw a horizontal line, just a very, very short one, and then use my protractor to measure 30 degrees and do a little angle there. Then I'm going to decide on a sensible scale. So here my force is 2,000 newtons. I probably don't have room on the exam paper to draw a line that's 20 centimetres long, but I might be able to do 10 or definitely 5. So I'm going to pick a sensible scale and draw my line appropriately. Now I need to make that horizontal line be long enough to sort of come directly underneath the end of that diagonal line. So as if I was going to draw a right angled triangle. and I'm going to use the scale that I've worked out to measure that line and find out how large that force is. And then likewise, I'm going to need a vertical line. So you could actually make this into a right angled triangle, but traditionally we would draw it over where the line starts. And I'm going to measure that one as well and use the scale to determine what the size of those angles are. So here it would be 1,730 newtons to the right and 1,000 newtons to the vertical. In order to describe how these resultant forces cause objects to move, we now need Newton's first and second laws of motion. The first law tells us that when the resultant force on an object is zero, acceleration is zero. Now that doesn't mean that the object is stationary. It's not velocity or speed that's zero, it's acceleration. So this means that its movement isn't changing. So if it's already stationary, it will stay stationary, but if it's already moving at constant speed, it will continue to move at that constant speed. Newton's second law of motion tells us that the acceleration of the object is proportional to the resultant force acting on the object, which means that if I push it twice as hard, it will accelerate twice as much, and therefore its acceleration is inversely proportional to the mass of the object. So if I have an object that is 3 times heavier, and I push it with the same force, it will only accelerate by 1/3 as much. This leads us nicely into the equation force is mass times acceleration. Make sure that you know the units for each of these quantities, and also make sure that you understand that meters per second squared is all 1 unit. So the squared is part of the unit and it doesn't affect the number. If you're given an acceleration of 10, you're going to be using the number 10, not using 10 squared. Also, remember that acceleration is a vector, which means that it has a given direction. So therefore it can be a negative number, and that would show you that the object was slowing down. The second force is required practical, which I'm actually talking about before the first one because I've done this in the order I teach it in rather than the order in the spec, is all about acceleration and how, as we've just seen, acceleration is directly proportional to the force that causes an object to accelerate. So the typical way to demonstrate this in the required practical is to use an air track and a glider. And the point of using this system is that it's basically frictionless, so we don't need to worry about taking friction into account. That glider is then attached to a pulley system with a weight on the end. So when you drop the weight, that is causing the force that makes the glider accelerate. And then we use 2 light gates. So these are basically laser beams that the glider is going to break as it goes through them. And based on the fact that we know how long the glider is, and the light gate will record how many seconds or partial seconds the beam is broken for, we can work out the velocity as it passes through each of those 2 gates. So that gives us an initial velocity and a final velocity, and we can use those to work out the acceleration. And then we'd repeat this experiment multiple times, changing the size of the force that causes the glider to accelerate. And we can do this very simply by adding more weighted masses to the end of that pulley. You may be asked to complete estimations about speed and acceleration and forces involved in everyday road transport, so it's worth having some ideas in your head about what typical speeds would be. And bear in mind that you probably know speed limits in miles per hour rather than meters per second. So it's worth knowing that there's about half a metre per second in a mile per hour. It's also worth being aware that cars tend to have a mass of around 1,000 kilograms and lorries tend to be about 40 times heavier than that. When a force causes an object to move through a distance, work is done on the object. So a force does work on an object when the force causes that object to be displaced. Again, you need to be familiar with all of the units for this equation because you may not be explicitly told this number represents work done. Deformation means changing the shape of an object, and it happens when more than one force is acting on an object, because if there were just one force, then the object would move rather than change shape. Deformed objects can be separated into those that are elastic and inelastic. Springs are elastic in nature. This means that when they're stretched by a force and then the force is removed, they return to their original length and size. Inelastic objects can be permanently deformed and they don't return to their original size when the force is removed. In reality, a spring isn't elastic forever. Every spring has something called a limit of proportionality, or an elastic limit, and if you exert a force that is greater than that, then it won't regain its original shape when that force is removed. You've probably seen this if you've taken a spring and you try and pull it too hard, and eventually it just opens up until it's a curly piece of wire and it doesn't snap back to being a spring anymore. When they're stretched, or indeed squashed, springs can be used to store energy. When we do work on a spring by giving it energy, the energy is transferred into the elastic potential energy store of the spring. The amount of work done in joules equals the amount of elastic potential energy stored in joules. This is because energy is conserved, which means it can be transferred between different stores, but it can't be made or destroyed. This energy can later be transferred to other stores when the spring returns to its original length. If the spring has not reached the limit of proportionality, then we can calculate how much elastic potential energy is stored in it using the following formula. Extension isn't the total length, it's the change in length compared to when there was no force acting on the spring. We can calculate it by taking the final length of the spring and subtracting the initial length, the length before we did anything. We can also use a mathematical relationship called Hooke's law to make predictions about how much a spring will extend by when a force is applied, or to work out what force has been applied when we know how much the spring has extended by. This is how Newton meters and certain types of weighing scale work. Hooke's law says that the force applied to a spring is proportional to how much it extends by. Proportional means that if I double the force applied, the extension will also double. The equation that we need to take that general proportional relationship and turn it into numbers for a particular spring is this one. Here we can say that the force applied is equal to the spring constant, which is a number for that one particular spring you're interested in, multiplied by how much it has extended by. Again, it's always extension, not length. We're interested in how much longer the spring has got. The mathematical relationship of Hooke's law will hold until the limit of proportionality is exceeded. This basically means that the spring will keep on stretching in a proportional way until it hits that limit, and then at that point it may stretch exponentially. You'll have seen this happen while investigating the required practical around Hooke's law. In this required practical, you would have had a spring that was suspended, probably using a clamp stand and a clamp, and then you would have hung masses off it, and you would have used a ruler to measure the extension, and probably used a Newton meter to calculate the force exerted by the masses that you were adding. When you did the required practical, you may have displayed your data on a graph like this, but there's one thing about this graph that is quite unusual. In science, we always put our independent variable, the thing that we're changing, on the x-axis, and our dependent variable, the thing that we're measuring, on the y-axis. But when you did this practical, you almost certainly hung masses with a particular weight on the spring, and then only afterwards measured the extension. So why have we flipped the axes in this graph? Well, there are two reasons. One is that it is possible to do the practical the other way round. You could stretch the spring until it's a certain length, and then see, using your Newton meter, what force is required to get that extension. But the other reason is actually a mathematical one. If we plot extension on the x-axis and force on the y-axis, like we have here, then the gradient of the graph, dy by dx, is force divided by extension, newtons divided by meters. So that's the units for spring constant, and the gradient of our graph is the spring constant. If we plot the graph the other way around, then the gradient of the graph is 1 over the spring constant, and suddenly you have another step to do in order to work out what the spring constant is for a particular spring. From this graph, we can easily identify where the limit of proportionality is. As long as Hooke's law holds, extension and force are proportional to each other, which means the graph has a continuous gradient, so we have a straight line. At the point at which the line stops being straight, we've passed the limit of proportionality. If you do choose to plot your data with force on the x-axis and extension on the y-axis, then you need to be aware that rather than extending exponentially to the right, the graph will extend exponentially upwards when it reaches the limit of proportionality. This is mainly important if you're asked to draw a sketch graph in the exam. If they give you data to plot, then it will be really obvious what's happening. The next topic is about how forces affect the motion of objects, and we start off with distance and displacement, and these often confuse students because they do sound really similar as concepts, because they're both to do with how far you're travelling away from a starting point. I like to think of distance as the number of steps that it actually takes you when you go on a journey, whereas displacement is about how many steps it would take you to get back home in an emergency. So if we imagine that we're starting off at the house at the bottom and we're going on a journey to get to the house at the top, but we're not going straight there, we're going to go on a little roundabout route. So we're going to travel 400 metres to the house on the right and then 400 metres up to the house at the top. So my distance is 800 metres because I've taken 800 metres worth of steps on this journey. But if it's an emergency and I have to get home as quickly as possible, I wouldn't go back via that house on the right, I'd just go straight there. And so my displacement is only 400 metres. In a similarly confusing way, speed and velocity both tell you something about how fast an object is moving. But whereas speed could be in any direction and is therefore a scalar quantity, velocity is in a particular given direction, so it's a vector quantity. That means that if I run at 5 meters per second due north, and I then turn around and run at 5 meters per second due south, my speed is still the same, it's 5 meters per second. But because the velocity is being defined as speed to the north, when I turn around and run in the opposite direction, my velocity will now be minus 5 meters per second. Although speed, distance and time do have standard international units like everything else, and we're often going to see questions that express distance in terms of meters and speed in terms of meters per second and time in terms of seconds, you should also be aware that we can make these compound units for speed out of any units for distance and time. So for instance, you could have a question in which the distance is given in kilometers and the time is given in hours, and therefore you'd be expected to work out the speed in kilometers per hour. You're also expected to know some typical speeds for walking and running and cycling. So this is what these are. Acceleration is another vector quantity, and it has to do with the change in velocity. You may not be explicitly given the change in velocity in the question. It's much more likely that you're given a final velocity and an initial velocity, and you have to work out what the difference between them is. So you could have something like, I was cycling at 5 meters per second, and then I accelerated to be cycling at 12 meters per second. So there you would need to see that the difference between 5 and 12 is 7, and that would be my change in velocity, and I would then divide that by the time to work out the acceleration. They could also make this slightly more challenging by not giving you either the initial or the final velocity and just referring to the object being stationary, in which case the velocity is obviously 0 meters per second. Remember, acceleration is a vector, so again it has direction, and if you have a positive number that tells you that you're speeding up in the direction that you're travelling, and if you have a negative acceleration that tells you that you're actually slowing down again. And then of course you do need to know your units for all of the different quantities. Next, we come to two different kinds of motion graph, and it's really important before you start answering any questions where they give you one of these graphs that you've identified whether you're looking at a dt graph with distance on the y-axis or a vt graph with velocity on the y-axis. Often the best way to answer these questions is not to think about having learned general patterns, but to look at what the graph is actually telling you. So what has happened to the distance, or what has happened to the velocity, and then just answer based on that. We can use these motion graphs to tell us about the motion of an object both in qualitative terms and in quantitative terms. If we think first of all just about the general shape of a graph, for a dt graph where we have a horizontal portion, this tells us that the object is stationary. So if I look at this, I can say that at point B, the object is 3 kilometers away from where it started, and then at point C, it's still 3 kilometers away. So it hasn't moved anywhere, therefore it's stationary. If we now look at the section from A to B, I can see that it started out at the starting point at 0 kilometers away, and then at point B, it's then 3 kilometers away, so obviously it's moved. And the fact that the line is diagonal tells me it's moving at a constant speed, so it's not accelerating, it's not decelerating, it's just going at this one constant speed. Then if I look at the line from C to D, I can see that it's steeper, and this tells me that it's now moving at a faster speed than it was before. Now, in terms of numerical calculations, we know that speed is distance divided by time. So if I want to work out what the speed is at a particular point, I can use the gradient of the graph to tell me that. So if I want to calculate the speed from C to D, I need to do distance divided by time. So I firstly need to work out how far it's travelled, not in total, but just between points C and D. So I'd say it finished off at 12 kilometres, but it started at 3, so the change there is going to be 9. And then likewise, we finished at the 12-hour mark, but we started at the 8-hour mark, so that's going to be a difference of 4 hours. So if I do 9 kilometres divided by 4 hours, I get 2.25, and because that distance and that time are in kilometres and in hours, my speed would be in kilometres per hour rather than in metres per second. If the graph curves rather than being a straight line, then we know that the object doesn't have a constant speed. But we can still use that same calculation to calculate the mean speed over the entire portion. However, if you're taking the higher tier, then you should also be able to draw a tangent and use that tangent to calculate the speed at any particular point on the graph. Remember, your most accurate calculations are going to be when your tangent is as long as possible. So we draw a tangent like this, so it's a long straight line that is just touching the graph at the particular timestamp that they've asked us to calculate. If you're struggling to draw a tangent that is accurately tracking the graph, what I tend to do is put my ruler on top of the curve rather than underneath it. And particularly if you have a ruler that's not see-through, that can make it a lot easier to make sure that it's touching the graph only in one place. So here's my tangent, and you can see that it's just touching the graph at the time of 15 seconds. And then I want to do the change in the y-axis divided by the change in the x-axis. So here for my y-axis, I've gone 1300 take away 400, which is 900 meters. And then my change in x is 25 seconds. So I know from my maths that to work out the gradient, I'm going to do 900 divided by 25. And therefore I get a gradient of 36 meters per second. And this time my units are meters per second because the distance is in meters and the time is in seconds. A VT graph looks a lot like a DT graph, but now the y-axis is velocity rather than distance. And again, I'd encourage you to just think about what the numbers are telling you rather than trying to learn a particular pattern. So here, if I look from B to C, I can see that the velocity starts at 6 meters a second, it ends at 6 meters a second. So obviously that object is traveling at a constant velocity. If I wanted to show that the object was stationary, then that line needs to not just be horizontal, but also be at 0. So that's what we can see from E to F. If the line is sloping upwards, say from A to B, the velocity goes from 0 meters a second to 6 meters a second. So obviously the velocity is increasing. So if the line slopes up, then the object is accelerating. And if the line slopes down, as it does from D to E, then the object is decelerating, it's slowing down. And also the steeper that line is, the higher the acceleration is. So I can say that the object is accelerating faster from C to D than it is from A to B. If I want to calculate how far the object has travelled, then I need to calculate the area under the graph. And I can do this using just my normal math skills of working out the areas of rectangles and triangles. It goes without saying that moving objects need some time and some distance in order to stop. If you've spent a lot of time on the motorway, then you'll be aware that lots of motorways have these white chevrons which are spaced 40 metres apart. And the idea is that cars should always have 2 of them between them. In other words, they should always be at least 80 metres behind the vehicle in front. Stopping distance is made up of 2 different components called thinking distance and braking distance. Thinking distance is the distance that the vehicle travels during the driver's reaction time, so not really while they're consciously thinking about whether or not they want to stop, but during the amount of time that it takes for an electrical signal to get from their brain down to their foot. Then the braking distance is the distance that the vehicle travels while it's under the braking force, so while the driver's foot is on the brake pedal. Here are some typical thinking and braking distances for cars travelling at various different speeds. As you can see, at 30 miles an hour, a car has a typical stopping distance in total of 23 metres, whereas by 70 miles an hour, it's more like 96 metres. Your reaction time is the time taken for a signal from your brain to reach your muscles, and it does vary from person to person, from about 0.2 seconds to 0.9 seconds. You'll have measured this as part of the biology required practical in the homeostasis topic. Reaction time can be increased by tiredness, drugs, alcohol, and just by being generally distracted. Thinking distance will be increased by anything which increases your reaction time, so we've just said tiredness, drugs, alcohol, and distractions. But thinking distance is also affected by the speed at which you're travelling, because the faster you're moving, the more distance your vehicle will cover before the signal reaches your muscles in order for them to brake. The link between speed and thinking distance is directly proportional. Here you can see that at 30 miles an hour, there's a thinking distance of 9 metres. And then if we double that speed to 60 miles an hour, then the thinking distance becomes 18 metres, which is also doubled because it's a directly proportional relationship. If we plot these 2 quantities on a graph, we get a straight line graph which passes through the origin, 0, 0. And that's how we can tell that it's directly proportional. As we double one quantity, we also double the other. If we now look at braking distance, we can see that that isn't the case, and this isn't a directly proportional relationship. If I consider the braking distances at 30 miles an hour and 60 miles an hour, we can see that actually the braking distance at 60 miles an hour is nearly 4 times larger, even though the speed has only just doubled. So we can say that an increase in speed affects the braking distance much more than it affects the thinking distance. One reason for this is the amount of kinetic energy that the car has when it's moving that quickly. If we take a car with a mass of 1,000 kilograms and we say that it's moving at a velocity of 10 meters per second, then it has 50,000 joules of kinetic energy, and it needs to lose that kinetic energy in order to come to a stop. But if I have the same car moving at a velocity of 20 meters a second, so twice as fast, it actually has 4 times as much energy that it needs to dissipate. When we're trying to explain this, we can say that a car travelling at a faster speed or a faster velocity has more kinetic energy, so therefore more work has to be done in order to stop the car. And when a force is applied to the brakes, the work is done by the friction force between the brakes and the wheel. We can calculate the size of the work by looking at the force and the distance. Now, this also helps us to explain why braking at high speeds can be really dangerous because it can lead the brakes to overheat. This is because the work done by the friction force, although it's reducing the kinetic energy, will also raise the temperature of the brakes, and so if the braking force is too large, the brakes may overheat and the car may skid. We've said already that travelling at higher speed was going to affect the thinking distance, but it also affects the braking distance. As we've just seen, a car travelling at a higher speed has more kinetic energy, so more work needs to be done in order to bring it to its stop. And so if we assume the braking force is constant, then a longer distance is required in order to bring it to a stop. Additionally, braking distance is going to be affected by wet or icy weather. It's important if this comes up in the exam that you're specifying the kind of weather and not just saying, oh, it's affected by the weather, because that could mean it's a sunny day and that wouldn't affect the braking distance at all. Braking distance will also be increased by poor tyre or poor brake condition. And again here, it's important that you're being specific and not just saying the condition of the car, but referring to the tyres and the brakes. You can think of momentum as unstoppability or oomph. We define it as the tendency of an object to keep moving in the same direction it was already moving in. Heavier objects have more momentum, and faster objects have more momentum. So if you know your units for mass and velocity, then we can put these together to make our units for momentum. So obviously mass is in kilograms and velocity is in meters per second. If we multiply those together, we get kilogram meters per second. You need to know that stationary objects don't have any momentum at all. In a closed system, momentum is conserved. In other words, the total momentum before an event is the same as after the event. This is true in a closed system, which means that over the course of the event, no matter and no energy gets in or out, and we can use this to make predictions about collisions and explosions. In this collision, one roller skater collides with another. If I know that my first roller skater has a mass of 75 kilograms and a velocity of 4.2 meters per second, then firstly I can calculate that initially her momentum is 315 kilogram meters per second. That will be a nice 1-mark question. Now, when she collides with the other roller skater, that same amount of momentum that she had at the start needs to be split between the two of them. In other words, they're not going to stop dead, they're both going to carry on moving, but because the momentum is split between the two of them, they're now going to move at a slower velocity than the initial velocity that the roller skater had when she was moving on her own. So let's say that I know that my second roller skater has a mass of 65 kilograms. That means that the two of them together, their masses come to 140, and that total amount of momentum is now going to be split between 140 kilograms. So we can solve this to show that their final velocity is going to be 2.25 meters per second. So they're both moving, but slower than the initial roller skater was when she was moving on her own. Don't forget that momentum is a vector, so it can have a negative value to show you that an object is moving in the opposite direction to the first object where you defined momentum, and this is important in order for us to be able to explain explosions. When we say explosion, we're not necessarily thinking of a bomb. We could just mean two objects moving away from each other in opposite directions, like a person on a wheelie chair throwing a heavy ball. But if you imagine that bomb for just a second, before it explodes, it has a momentum of 0 because it's not moving. But at the end of the scenario, obviously things are moving. Now, the reason that this can be the case is as long as you have something moving to the right with the same amount of momentum as something moving to the left, then the positive and negative momentum still add up to 0. So if we go back to our two roller skating friends and they're now stood touching and they push off each other and go in opposite directions like this, then we can work out that our roller skater on the left has got momentum of 975 kilogram meters per second, and therefore our roller skater on the right must also have momentum of 975, but this time it's a negative number because she's moving in the opposite direction. It doesn't matter which one I've made positive and which one I've made negative, just that one of them is positive and one of them is negative, so they still add up to 0. Then if I solve my momentum equation for the new figure, then I'm going to work out that the velocity of the second skater is minus 15 meters per second. It's a negative number because she's moving in the opposite direction. And if I think about it, if I do a little common sense check, that makes sense. It's kind of the same order of magnitude of velocity, but she's moving slightly faster because she's slightly lighter. Unit 6 is the waves topic, and we start off by saying that waves can be either transverse or longitudinal. In a transverse wave, the oscillation of the vibration of the wave is perpendicular to the direction in which the wave is travelling. In a longitudinal wave, the direction of the wave and the direction of the oscillation are parallel to one another, so they're going in the same direction. The ripples on the surface of water are an example of a transverse wave. Longitudinal waves show areas of compression, where the particles are close together, and rarefaction, where they're spread out. And sound waves travelling through air are an example of a longitudinal wave. You should be able to label a transverse wave to show peaks and troughs and wavelengths and amplitudes. We start out with the undisturbed position, or the equilibrium position, and onto that we can draw our transverse wave. Remember, a transverse wave is one in which the oscillation is perpendicular to the direction the wave is travelling. So my wave is going from left to right, but my oscillation is going up and down. On this I can label the peaks and also the troughs. The peaks are all the highest points and the troughs are all the lowest points, and once I have these labelled I can add in wavelengths. The wavelength of a wave is the distance between two equivalent points on two adjacent waves. So I can draw the wavelength from peak to peak, but I can also go from trough to trough. You could technically also go from one of the middle points of the wave, but it's really easy if you do that to actually accidentally only label half the wave, so I wouldn't recommend it. The one that people tend to get wrong is the amplitude. So remember that the amplitude is half the height of the wave. It's the maximum displacement of the wave from the undisturbed position. The other thing that you need to be able to identify is the frequency of the wave. So if this box represents 1 second, then there are 3 waves inside it. In other words, 3 waves have passed a point within a second, and the frequency is 3 Hz. Linked to this is period. The period is the time taken for one wave. So if I've managed to fit 3 waves into 1 second, then the period is going to be 1 divided by 3, in other words, a third of a second. Again, we have another calculation, so just make sure that you're familiar with all of the units for all of the different quantities. Also, we can calculate wave speed by multiplying together frequency and wavelength, and again, you need to know the units for these. Required Practical 20 is about making measurements of waves, either in a ripple tank or by looking at, say, a string with a signal generator attached. Now, there are lots of different ways that they could set up a question about this, but a typical way would be to ask you how you could collect data to allow you to calculate wave speed, in which case you're going to need the wavelength and also the frequency. Now, wavelength is literally a length and you can measure it with a ruler, particularly because if we're thinking about the ripple tank, you're going to have the places where the peaks of the waves are, there's more water underneath them, so less light gets through and therefore it looks darker. And then when you've got the trough and it's shallower, then more light can get through and it looks lighter. But obviously these waves are moving and that makes measuring them quite challenging. So the typical way to do this would be to place your ruler alongside the ripple tank and then take a photograph that includes that ruler. And then you can measure it on that static picture that you've got, but you've got the ruler in there for scale. Now, one thing you can do to make your data more precise is rather than just measuring from one peak to the next peak, measuring, say, 10 waves in one go and then dividing that length by 10. Next, you need to think about the frequency. Now, the normal way to use a ripple tank is to have some kind of oscillator or signal generator, which is causing a metal or wooden rod to bounce up and down and create the waves. And often that's going to have a screen on it and you can say, oh, I want a frequency of 2 Hz, in which case you could just read it off there. But if that's not available to you, then what you can do is pick a point and then count how many waves go past per second. And just like with wavelength, we're going to be more accurate if we measure over a greater time. So rather than saying how many waves went past in 1 second, you might say how many waves went past in 50 seconds and then divide it by 50. Once you've got those 2 pieces of information, you could put those together to work out the wave speed. Or if you were trying to work out wave speed firstly, then what you could do is have your ruler alongside the ripple tank, measure the time for one wave to travel the length of the tank by using a stop clock, and then use velocity is distance, so the length of the tank divided by time, and you could also work it out that way. Electromagnetic waves are transverse waves that transfer energy from the source of the waves to an absorber. All types of EM wave travel at the same velocity through a vacuum or through air. Electromagnetic waves form a continuous spectrum. In other words, there isn't something fundamentally different about a radio wave and an infrared wave. We just give them slightly different names depending on their particular frequency and wavelength. You can think of it a bit like how in a rainbow there isn't one set point where red turns into orange. We just give the colour a different name depending on its wavelength. Going from long to short wavelength or low to high frequency, the groups of waves are radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. Within that visible light portion, we start with red wavelengths, which are the longer wavelengths, closer to infrared, and then we finish up with the violet colours next to ultraviolet. Our eyes only detect visible light, so we only detect a limited range of those electromagnetic waves. Different substances can absorb electromagnetic radiation, in other words, take it in and not give it back. They can transmit it so that it passes through them. They can refract it so it changes direction as it passes through them, or they can reflect it so they can bounce it back. And the way in which they do this may depend on the wavelength. If you're just thinking about the visible portion of the electromagnetic spectrum, if you have a red object, then that red object reflects red wavelengths of light, but it absorbs all other wavelengths of visible light. Some of these effects, like refraction, are due to differences in the velocity of the waves in different media. In other words, the wave is travelling at a different speed if it's in a substance with a different density, and that's going to affect how it's refracted. You need to be able to show how refraction happens by drawing a ray diagram, and the typical example for this that you're likely to have done in school is a rectangular block made of glass or plastic, and you're looking at light going from the air into the glass block and then back out again. Your first step is to draw the normal, which is an imaginary construction line which happens at the point at which the light ray hits the block. Then we can add in the incident ray, so the light coming in, and the angle of incidence, which you need to remember comes between the ray and the normal, not between the ray and the block. And the way to remember this is that if you've gone to the trouble of drawing the normal, you need to use it for something. Now, light travels in straight lines, so if no refraction happened, we would expect the light to carry on in a straight line, but that's not what we see. The glass is denser than the air that the light was previously travelling through, and when light meets a denser medium, it bends towards the normal. So that's what we're going to see. And then when it reaches the other side of the block, it's now going from the glass to a less dense medium. So instead of bending towards the normal, we can draw a new normal here, it's now going to bend away from the normal. And because this block is rectangular and therefore the two sides of the block are at the same angle, what we're going to see is that the block is going to cause the light ray to refract back by the same amount that it refracted in the first place. So your incident ray and your refracted ray are going to be parallel to one another. If I had something like a triangular prism where the sides weren't parallel to each other, then I would find that although there is refraction on the far side, it wouldn't be the exact reverse. And therefore, because the different wavelengths of light actually refract by different amounts, I would end up producing a spectrum instead. The reason that the refraction happens is that as the wave enters the more dense medium, it slows down. Now, if the wave is travelling perpendicular to the surface that it's passing through, then the whole wavefront slows down equally. So the whole light ray slows down and then speeds up together, and you don't see any refraction. But where it hits the change in medium at an angle, the light ray basically pivots around that point. It's a bit like if you imagine if you're ice skating holding hands with someone, and then one of you suddenly stops, the other person pivots around them. The next required practical is about investigating how the amount of infrared radiation that's absorbed or radiated by a surface depends on the nature of that surface. This could be about the surface type, is it shiny or matte, or whether the colour makes a difference. In order to test this, you need a number of identical cans or hollow metal cubes. They need to have the same dimensions but different surfaces, and that's the independent variable. Everything else that could be changed needs to be kept the same, because otherwise we won't know whether it's the colour that's affecting the amount of infrared given off or whether it's something else like the surface area. You fill the cans or cubes with hot water from the same kettle, so they are starting at the same temperature, and then you use a ruler to position an infrared detector at a consistent distance away from the can. You don't want to have a situation where your infrared detector is 10 centimetres away for one can and then for a different can it's 20 centimetres away, because then you wouldn't get valid data. And then you use that infrared detector to take readings. You can also take the temperature of the water as a surrogate for this, because if the can is radiating more infrared, then its temperature will drop faster, but the data just isn't as valid. If you're taking higher tier, then you need to know that radio waves can be produced by oscillations in electrical circuits. When radio waves are then absorbed by an aerial, they create an alternating current, and that alternating current has the same frequency as the radio wave. So the radio wave can itself induce an oscillation in an electrical circuit. Changes in atoms and in the nuclei of atoms can result in electromagnetic waves being generated or absorbed over quite a wide frequency range. You already know from Unit 4 from Paper 1 that gamma rays originate from changes in the nucleus of an atom. Electromagnetic radiation can cause hazards, but how hazardous the EM radiation is depends on both the type of radiation and also the dose. Obviously, if you're exposed to a larger dose, then the hazard is higher. Infrared radiation is transferred from hot objects, so you can be burned by it. But UV radiation also causes skin to age prematurely, which is why you get wrinkly if you use tanning beds. And it also massively increases the risk of skin cancer. Both X-rays and gamma rays are ionising, and this can lead to the mutation of DNA and ultimately cancer. EM waves are really useful, and you need to know what each portion of the spectrum is used for. Radio waves are for both television and radio broadcasting. Microwaves can be used for satellite communications, like sending text messages, but also for cooking food in a microwave oven. Infrared radiation is used in electrical heaters, but also to cook food, and in infrared cameras, which can detect body heat for things like manhunts in the dark where the police are chasing someone. Visible light is used in fibre optic communication, like broadband. Ultraviolet is used in energy efficient lamps, but also for suntan beds, and then X-rays and gamma rays are used in medical imaging and also in treatments such as radiotherapy. The poles of the magnet are the places where the magnetic forces are strongest. When two magnets are brought close to each other, they exert a force on each other. So two like poles repel each other and two unlike poles will attract each other. Both attraction and repulsion between magnetic poles are examples of non-contact forces. A permanent magnet produces its own magnetic field. An induced magnet is a material that becomes a magnet when it's placed in a magnetic field. So for instance, this pin is being attracted to the permanent magnet, but it becomes a magnet as long as it's attached to it. So it can then attract a second pin. But the thing with an induced magnet is that it loses its magnetism as soon as it's removed from the magnetic field. So if we took that pin away from the permanent magnet, then the second pin would stop being attracted to the first one. A magnet's magnetic field is the region around the magnet where there is a force acting on either another magnet or a magnetic material. So there are three magnetic metals: iron, cobalt and nickel, but also we include steel because that's an alloy that's mainly made of iron. The force between a magnet and a magnetic material, say an iron nail, is always one of attraction. The nail is never going to be repelled. The strength of that magnetic field depends on both the distance from the magnet, so the further away you are, the less attraction there is, and also where on the magnet you are. So the field is always strongest at the poles of the magnet. When we're drawing field lines, the direction of the magnetic field at any point is given by the direction that the force would be acting on another north pole placed at that point. So if we think about the north pole of a bar magnet, that would repel another north pole, so the field lines are going to go away from the north pole. And then if we're at the south pole of the magnet, that would attract a north pole, so the field lines are going to be going in. The direction of the lines is from the north seeking pole of the magnet to the south seeking pole of the magnet. A magnetic compass contains a small bar magnet. The Earth also has a magnetic field, so the compass needle points in the direction of the Earth's magnetic field. Wherever a current is passing through a conductor, like a wire, a magnetic field is produced around the wire, and you can work out what the direction of that magnetic field is by doing a thumbs up sign with your right hand. So your thumb represents the flow of current through the wire, and then your fingers, as they curl around, represent the magnetic field. The strength of the magnetic field depends on the size of the current that's going through the wire, so if the electrons are moving faster, then we'll have a stronger magnetic field, and also the distance from the wire, just like with a permanent magnet. If you shape that wire into a solenoid, so into a coil, this increases the strength of the magnetic field created by the current. The magnetic field inside a solenoid is strong and uniform. In other words, it's not changing in different parts of the solenoid. So the overall magnetic field actually has a similar shape to that of a bar magnet. If we add an iron core into the middle of that coil of wire, then this increases the strength of the magnetic field, and we can start referring to this as an electromagnet. The final topic in the combined science papers is the motor effect. So if we take that conductor, something like a wire, and there's a current flowing through it, and we then place that in a magnetic field, then the magnet producing that field and the conductor are going to exert a force on each other. The reason that this works is, as we've just established, if there's a current flowing through the conductor, that conductor has a magnetic field too. So we've now got two magnetic fields cutting across each other, and they're going to interact, causing either repulsion or attraction, and therefore the conductor ends up moving. So this is called the motor effect, and we predict which way the interaction is going to happen and which direction the conductor is going to move using Fleming's left-hand rule. You need to hold out your left hand, and it has to be your left hand so that your first finger and second finger are at 90 degrees to each other, and then your thumb is also at 90 degrees. So you're sort of 90 degrees in 3D. Your first finger represents the direction of the magnetic field, which goes from north, where your hand is, to south at the end of your finger. Then your second finger represents the current, and it's important to remember that the direction of the current we're talking about is conventional current. In Unit 2, Paper 1, we talked about the fact that when electricity was first discovered, we didn't know it was electrons moving. So because we didn't know it was negative particles, conventional current actually goes backwards to what's really happening. So make sure you're aware of that when you're orienting your second finger. Then your thumb shows you the direction of the movement. The idea is that if you know the direction of the field and the current, you can predict the direction of movement. Or likewise, if you know which way the wire moves and you also know the direction of magnetic field, then you can predict which way the current is flowing, or whatever. As long as you've got two of the quantities, you can predict the third one. Now, a typical exam question might ask you to explain something like, why is it that a wire will move when you put it in a magnetic field? So you need to mention that the wire has a current flowing through it, because if it didn't have a current flowing through it, then it wouldn't have a magnetic field, and therefore nothing would happen. Then we need to talk about the fact that the magnetic field that's around the wire interacts with the magnetic field of the permanent magnet. And the final thing to say is that because of the interaction of those two magnetic fields, there is a force acting on the wire. A motor is made from a coil of wire which is carrying current in a magnetic field. So here's my coil of wire, and as you can see, there's the current moving around it in a circle, always from positive to negative, because remember, this is conventional current. And this coil of wire is placed in a magnetic field. This is made from either a U-shaped magnet, or we could use two separate static bar magnets, but either way we have north and we have south. This is going to cause that coil of wire to rotate, and in order to make this rotation continue always in one direction rather than flip-flopping back and forth between it, we need to add a split ring commutator. When the motor is turned on, the coil of wire is experiencing the motor effect, but because the current is moving around in a circle, because on the left side of my coil it's moving away from me and on the right side it's moving towards me, the force felt by the two sides of that coil is going to be opposite to each other. So the left side is going to be pushed down, whereas the right side is going to be pushed up, and this leads to rotation. So that's it for Physics Paper 2 of AQA GCSE Combined Science. I hope the video helped you to be a bit more confident, and if you haven't already, watch the Morning of Physics Paper 2 video for some last minute revision tips. If you have found this useful, then don't forget to like and subscribe.